Hello, chemists. It is the second video of the week. Last video was about gas laws, and we looked at how the gas laws worked, how they predict how a gas will change. If you change the pressure, it will change the temperature or the volume. We can predict and calculate all kinds of things about how gases will act using the gas laws. But the gas laws don't explain anything about why. So chemists looked at those gas laws and tried to come up with a theory to explain why. So after the gas laws, they tried to come up with this theory that explains why those gas laws work and what molecular explanations explain why gases act the way that they do. So we got the kinetic molecular theory explains the gas laws by the movement of molecules. Okay, so let me just break down kinetic molecular theory. This is a big term. We also, because it's a long term, a lot of chemists will just shorten it up to KMT. Let's just break the word down so we can make more sense. Kinetic, you've probably seen in physics. Kinetic means movement. And so I'm just going to turn this into a sentence. The movement. Molecular, well, you know what molecules are. We're talking about gas molecules in this case. So we've got the movement of gas molecules, and then a theory is just an explanation of a law. So this theory explains the gas laws. So overall, the kinetic molecular theory is the movement of gas molecules explains the gas laws. And that's what the kinetic molecular theory is. Okay, so I need to do some of the actual use the scientific verbiage. So let me show you the actual scientific verbiage, and then I will break it down and do some analogies and spend the rest of the time trying to understand what these four postulates mean. So when they made this theory, they came up with these four things that had to be true in order for a gas to act like we see in the gas laws. So these are the four things that explain why if these things are true, then gases will act like we see in the gas laws. So the first one is a gas consists of many small particles which have such a small volume compared to the overall volume of the gas that the volume of the particles is insignificant. So I'm going to break this one down specifically later, but I just want you to picture you've got this imagine you've got this tiny little atom of gas, right? Or a molecule of gas even. And so imagine it is so small that the space around it is mostly empty, and the volume of the overall space that it's in is way bigger than the volume of the little bit of gas. And we'll see what that looks like more specifically. Okay, the second one is the particles are in constant motion. So I want you to picture this same little dot of gas, and it is moving much like I want you to picture that you've got super balls. You ever play with those little super balls? They're crazy bouncy, those super bouncy balls. I used to love those things. Anyway, so imagine you've got super balls, so that if you start bouncing one of them in a room and then close the door of the room, walk away, come back the next day, it's still bouncing in there, bouncing around off the walls and everything, even after a day. So that's what I'm talking about. Like, they just keep on moving. They don't slow down. They keep on bouncing. So I want you to, like, I can't even do it with this thing, but they're bouncing off the walls of the container. They're bouncing off each other, and they just keep on bouncing. And what's happening is every time they bounce off the wall of the container, that is pressure. Or if there's something in the container and they're bouncing off of it, that is pressure. It's those collisions with the walls of the container or with the other stuff inside the container that is the pressure that we feel. If you feel air pressure on you, it's because the air is bouncing off of you. Okay, so that is the particles in constant motion. Okay, the particles exert no forces on each other. They do not attract or repel each other. So what I like to think about is those perfect bounces. Imagine those little super balls. They bounce perfectly off of each other and never stop moving. So you could also picture like a pool table with perfect bouncing billiard balls, and they bounce off the sides of the table perfectly, and they don't slow down. They just, so imagine you break the what do they call that? Anyway, you break for the start of a game, and then you walk away, and then you come back a day later, and they're still bouncing off of each other. Hopefully they haven't fallen in. Eventually, I suppose some of them would fall in the holes, but let's imagine there's no holes and no place for them to go in, and they keep on bouncing off of the walls of the container and do not stop. And they bounce off of each other without getting stuck together. They bounce off the walls of the container perfectly. All these are perfect bounces. The fourth one is the temperature in Kelvin is proportional to the kinetic energy of the gas. And I want you to, we got to think all the way back to Kelvin. Remember, we measured temperature in Celsius, but we also measured it in Kelvin. Kelvin is the one that, like, you can go all the way down to absolute zero. Absolute zero is a measurement in Kelvin. It's the lowest temperature that exists in the world as far as we know, and there's all kinds of crazy theoretical stuff that happens at absolute zero. They're still trying to guess what actually happens at absolute zero. Anyway, so we got absolute zero is the lowest temperature you could possibly go, and then Kelvin is measuring up from that. So 0 degrees Celsius is, if you remember, 0 degrees Celsius is 273 degrees Kelvin. So at 0 degrees Celsius, we are 273 degrees above absolute zero. And so the measurement of temperature in Kelvin is proportional to the kinetic energy of the gas. And that means that how fast those molecules are moving is proportional to what the temperature is in Kelvin. So if you heat it up, those molecules will move faster. If you cool it down, the molecules move slower. So an example of that is helium at room temperature. You just have a bunch of helium in a balloon, just a typical helium balloon at room temperature. The average speed of one of those helium atoms is at least 1,300 meters per second. Now you might be like, well, that's not that fast, is it? I mean, well, how fast is 1,300 meters per second? That's 8,000 miles per hour. And now you could be like, well, is that really that fast? Well, a 777 jet goes about 250 meters per second. A regular bullet goes about 200 meters per second. And the fastest, high velocity cartridges bullets go about 1,200 meters per second. So those little helium atoms inside of a regular old balloon at room temperature are going faster than the fastest bullets inside of that balloon. So they move pretty fast. And if you heat it up, they will go even faster. Okay, so we got to do some imagining to try to picture what those postulates really mean. So I'd like you to do some little imagining with me. So imagine that you're back at Harbor City and we're inside the chemistry classroom and you're sitting in your chair and you say, oh, so nice, isn't it? We can actually do chemistry and actual labs. Anyway, you're in your chemistry classroom, you're sitting in your chair and you say hi to your seatmate, you just wave hi to your friend across the room. Okay, so we're in the chemistry classroom and now we are going to magic school bus the whole room down. So all of us inside the chemistry room, we are going to get magic school bused, shrunk down. So shrink us all down so that we are small enough that helium gas atoms are the size of wiffle balls. So we shrink down so that here's a wiffle ball. If you were holding a wiffle ball in your hand and you saw a helium gas molecule, we let a helium gas atom into our room, it would be the same size as this wiffle ball. Okay, so picture that. Now, what I want you to imagine is if it was a typical room temperature helium balloon at regular old pressure, how many helium atoms would be inside of the chemistry classroom if they were the size of these wiffle balls? I'll let you think about that. Picture the classroom. You're like, how much space do they have between them? How many of them would be packed inside our classroom? Just kind of typical, typical space between them all, between the atoms. Okay, the answer is there'd be 10. There'd be 10 wiffle balls or 10 helium atoms in the chem classroom. Compare the size of the room. That's about how far apart they are. And now I want you to picture them as super bouncy. And 10 of you throw those wiffle balls around the room and they bounce off of you and the walls and everything else in the room. Oh God, it's a mess. But anyway, imagine the wiffle balls are bouncing off the wall really, really, really fast. But anyway, every time they hit the wall, that's pressure. Every time they hit you, that's pressure. Okay, so we've got 10 wiffle balls in the chem classroom, and you notice that the size of those wiffle balls is pretty small compared to the overall size of the room. So that is the first postulate. We're doing the postulates of wiffle balls, but the first postulate of the KMT is that the helium atoms are very small compared to the size of the container that they're in, or the space between them. Okay, so then let's do the next postulate of wiffle balls. So we've got those same helium atoms, those 10 helium atoms in our chem classroom that we've shrunk down to the size of helium atoms. We've got the wiffle balls are in constant motion. They're bouncing off the walls and bouncing off of us. And every time they hit a wall or hit us, that is what pressure is. And you can kind of picture it, like those things hitting you. That would be, and they're going really fast. That's a force pushing on you. Okay, so then the wiffle balls are not attracted to or repelled to each other. Imagine them as perfect super balls. They're bouncing off each other, bouncing off you. If we all left the room, which we probably would if they were moving that fast, we'd get the heck out of the room, close the doors, and just let them bounce off of each other. If we came back a day later, they'd still be doing that. They'd still be bouncing off each other and bouncing off the walls, and that's how that works. And then those 10 wiffle balls, if they were at room temperature, well, they'd be moving. Now, I don't know how to do the conversion, but if they were just regular old helium atoms, they'd be moving at 1,300 meters per second, which would be, oh my goodness. Yeah, they're really fast. Imagine they're just crazy, crazy fast. So they're bouncing off those walls so fast and bouncing off of each other. And if we heated up the chemistry room, they'd go faster. If we cooled it down, they'd slow down. Okay, so then let's just think about the variables that we were looking at for ideal gas laws. Temperature, T stands for temperature. Temperature is the speed of the wiffle balls. If we increase the temperature, they all go faster. Pressure is, do you remember what that is? How do we, what does KMT explain pressure is? Pressure is the speed and the number of collisions. How hard do they hit the walls and how often do they hit the walls of the container that they're in? And then V is volume. What is the volume in our little example here? The volume is the space that the wiffle balls or the helium atoms are in, and that's the volume of the room or the volume of the container that they're in. Okay, and then N, we use that as a variable for the number of gas molecules. N is the number of gas molecules, and usually we measure that as the number of, it would be the number of wiffle balls. In our case, it would be the number of helium atoms, but usually we measure it because there's not just 10. I mean, usually when we're measuring amounts of gas, we're talking in moles. So that would be the number of moles of gas molecules. Okay, let's use the kinetic molecular theory and those postulates to see if we can explain why we see this relationship between pressure and volume. Why is it that as we increase the volume, the pressure goes down, or if we decrease the volume, the pressure goes up. Let's see if we can explain it using the kinetic molecular theory. And I think we can. If we decrease the volume, we just gone here, we've decreased the volume here, we've made these guys squished into a smaller space. Now, if they're squished into a smaller space, that means that these particles, can you picture them hitting the walls of the container more often, right? Twice as often as when they're all spread out like this. So if we have the same number of molecules, same temperature, but decrease the space that they're in, they're going to hit more. They're going to hit the walls more often. I like to think of it like a mosh pit. You know, like you got all these people bouncing off of each other. If you give them more room, they'll hit each other less. But if you squish them into a tiny little ball, they're going to hit each other very often. Anyway, so that is the pressure and the volume explained by the kinetic molecular theory. So as volume increases, the pressure decreases because as the volume increases, they hit the walls less often. Okay, so how does volume and temperature get explained by the kinetic molecular theory? Here we got these guys going very fast and these guys going very slow. And the pressure is how often they hit the sides of the container. Can you see how if we take the same number of molecules, but we heat them up twice as much, these guys are going to, if they're going twice as fast, they're going to hit the walls of the container about the same as these guys who are squished closer together but moving slower. So particles moving faster, so they hit the wall with more force and more often, so they push on the container to increase the volume. And the pressure is the same if we increase the volume, so they can kind of even it out. So as temperature increases, the volume increases. Okay, let's see pressure and temperature. We've got this at regular room temperature, and then we heat it up, but we don't let it get any bigger. The volume of the container is the same, but these guys are moving a lot faster and hitting the walls a lot harder and a lot more often because they're zipping around a lot. These are just kind of hitting the walls a little bit, you know, every once in a while. So that means that they're hitting the walls more often. They have increased the pressure. Does that make sense? So the particles are moving faster. They hit the wall more often with more force, and that means increased pressure. So as temperature increases, the pressure increases if the volume doesn't change at all. Okay, so let's see if this makes sense. If you put more molecules inside of a container, that means it needs to take up more space. The volume has to increase in order to allow them to hit the walls about the same rate. So you think about these, they have to be the same temperature, but then they also have to be about as spread out so they hit the walls at about the same rate as when they were in the smaller container, right? So as the number of molecules increases, the volume increases. Okay, so I think we got the same thing. If we have more molecules squished, twice as many molecules squished inside of this volume, that means that they're going to be hitting the sides twice as often as these guys, because there's 2 times as many molecules in here. That means they're hitting the walls more often. That means more pressure, or twice as much pressure as the yellow one, and more particles to hit the wall more often, so that increases the pressure. They're the same temperature and volume, but the number of molecules has changed, so the pressure has to increase. So it doesn't matter which gas it is, it's just the number of particles. So as the number of molecules increases, that means the pressure has to increase. Okay, so I think that's it. I'm just going to put these 4 up here so you've got them, and I think these help us understand why gases act the way they are. And you can explain all of these different demos, all of these different observations that you see about gases using the kinetic molecular theory to explain why the gases do what they do. Okay.